So we're going to show an example problem with several different forms of mechanical energy. This problem is going to have a spring which has elastic potential energy. It's going to have a moving object which has kinetic energy, and it's going to have that object changing its height above the ground, which means we're going to have to deal with gravitational energy. So this is a problem from the Knight textbook, Chapter 10, Problem 63. A 50-gram ice cube can slide without friction up and down a 30-degree slope. The ice cube is pressed against a spring at the bottom of the slope, compressing the spring 10 centimeters. The spring constant is 25 newtons per meter. When the ice cube is released, what distance will it travel up the slope before reversing direction? So it's a really good idea to make sure you can draw a picture, especially in a problem like this where there's a lot of things going on. And I'm interpreting this problem with the picture shown here. So I'm interpreting that at the beginning of the problem I've got an ice cube which is at the very bottom of the slope, and the spring is already compressed, and I'm showing that here. So we measure the position of the end of that spring by a coordinate x, and I'm calling the initial x of that spring negative 10 centimeters, negative because the spring has been compressed. If it had been stretched, that would be a positive 10 centimeters. I'm also showing next to that what the meaning of that 10 centimeter compression is. I've just drawn an uncompressed spring. X would be 0 at the position where that spring is uncompressed. So this block actually is going to leave that spring after it's moved up the slope a little bit, 10 centimeters. All right, but the block is released right down here. And I'm going to add one more thing to my picture. We're going to assume that the block is released from rest, so the initial speed of that block is 0. Okay, the other stuff I've showed on my diagram, I've got to be careful about thinking about the relationships among the different distances. So the ground at the bottom of that slope, I'm going to define my ground to be 0 vertical position. Y initial will be 0. Y represents my vertical position. And it's always a good idea in conservation of energy problems, which this one is, to pick the lowest place in the problem and call that position vertical position 0. And then this problem ends when the ice cube is somewhere higher up the slope and it's gone a vertical distance y final. But we don't know what that is. But we do know when the block gets there that it's going to stop. Okay, that's the highest it's going to get. So its final speed will be 0. And then one more thing I've showed on the diagram. The problem asks what distance will the ice cube travel up the slope. That means the distance along this hypotenuse here, along this direction of the slope. And I'm going to call that distance capital D. And hopefully you can see I've got a right triangle here in my picture, which I'm going to have to use. All right, we'll come back to the picture in a minute. So now let's talk about how to set up conservation of energy problems. So after you draw your picture, you want to define your system, and you usually want your system to contain all of the important objects so that it's an isolated system with no work being done on it, so we can say that the total energy of the system is conserved. So in this problem, what kinds of objects do we want to include? Well, there's an ice cube. That's important to include. I'm going to try to focus this right now. There we go. Well, that's not very good. try manual focus. That's a little better. There's an ice cube, and that's what's going to have our kinetic energy. There's a spring, and that's what's going to have what I'll call U elastic. It has elastic potential energy. And then we want to put the Earth in our system because it's the system of Earth plus ice cube that interacts with a gravitational interaction. And that system will have U-grav, which is gravitational potential energy. And if you wanted to, you could also put the ramp in the system. Let's go ahead and do that. If we didn't do that, then the ramp would actually be exerting a force on the ice cube. And that force, we'd have to talk about the work done. So I'm just going to put the ramp in the system. Alright, we also want to be clear about the state of the system at the beginning and end of the problem. So I'll just make a note here. The initial state, we have an ice cube at the bottom of the hill, call it a ramp. We have a spring that's compressed. Alright, the final state, we'll have the ice cube at its highest point. The spring will be uncompressed. It'll be in its natural length. Okay, so when we do conservation of energy, we want to write down our work-energy relationship. The net work done by any external forces will equal always the change in energy of our system. Change in energy means the final energy minus the initial. And because we made our system an isolated system, the net external force will be 0. And since work is force, absolute value, times distance that the system travels, absolute value, times cosine theta. I'm going to assume you know where that formula comes from. The work will be 0 because the force is 0. And the whole point of setting it up this way is that now we can say that our system's energy doesn't change, its initial energy equals its final energy. Okay, going back to our system, we know that there are 3 kinds of energy happening inside this system. And I'm going to put all 3 of them into my energy equation. I've got kinetic energy, I've got elastic energy, I've got gravitational energy. I've got to add those together to find the total. I've also got at the end kinetic, elastic, gravitational. Okay, now I know a formula for each of those forms of energy, and hopefully you've studied those. So let's put in the formulas. Kinetic energy is always calculated by 1/2 times an object's mass times the square of its speed. Elastic potential energy of a spring, an ideal spring, is calculated by 1/2 times the spring constant K times the amount the spring is stretched or compressed squared. And the gravitational energy of an object Earth system is always calculated by the mass of the object times little g times the height of the object above the Earth. Alright, I'll put those same formulas on the right hand side. And now we're just going to finish the problem. So we can simplify this. A lot of these things are 0. We said that the block wasn't moving at the initial state of the problem, so that means the kinetic energy is 0. And we also defined the initial height of the block above the Earth to be 0. So that's 0. On the right-hand side, the end of this problem is the instant when the block is at its maximum height. So its final speed is 0. And because the spring will no longer be compressed at the end of the problem, x final is 0. So that's 0. So really this is a problem about converting the initial elastic potential energy of the spring into the final gravitational energy of this ice cube plus Earth. So I'm going to simplify this and start solving that out on the next page. So we have 1/2 times the spring constant times x initial squared equal to the mass of the ice cube times g times y final. Now the goal was to find that distance d. So on our picture, we're going to do some trigonometry here. We can see that we have a right triangle. This is a perpendicular 90-degree angle. So d is the hypotenuse, and this side, which is that distance represents how high the ice cube went, is the opposite side to this angle theta. So we're going to use sine of theta, which is always opposite divided by hypotenuse. In this case, that will be the opposite side is y final, the hypotenuse is d. And I know the angle theta. So that's going to let me solve for a relationship between y final and d. And I'll put that on the other side. So we know that sine theta equals y final over d. Therefore, y final is d times sine theta. And I'm going to put that into my conservation of energy. So that gives me 1/2 k x initial squared equals to mg times d sine theta. And now I can solve for my goal, which was solving for d. That's going to be d equals k xi squared divided by 2 mg sine theta. And now I can put in my numbers in units. The spring constant was 25 newtons per meter. The initial distance the spring was compressed was 10 centimeters, which is 0.1 meters. And I've got to square that. Divide by 2. The mass of the ice cube was 50 grams, which is 0.05 kilograms. Little g, which is 9.8 meters per second squared, and the sine of 30 degrees. And if I put all of those into my calculator, I find that d is 0.51 meters. So that's the answer. Okay, I hope you've understood the procedure for setting up a conservation of energy problem that includes 3 kinds of energy, 3 kinds of mechanical energy: elastic potential energy, gravitational potential energy, and kinetic energy.